Hello and welcome to INE's webinar for the basic L3 VPN implementation with the PEC routing protocol as BGP. For some of you who do not know me, I am Rohit Pardasani. I'm a full-time instructor with INE. Have about 5 CCIEs, CCIE route switch, security, voice, collaboration, and service provider. Now, in this video, or in this webinar, in fact, we are basically going to be talking about the need for L3 VPN and what are the prerequisites to build a successful L3 VPN. We would not be talking about L3 VPN with inter-AS because of obviously time constraint, but we would talk about implementing L3 VPN with a single infrastructure or single service provider. So if you look at BGP, MPLS, L3 VPNs, it's basically an alternative to IPsec VPNs. IPsec VPNs requires you to configure full mesh. It does give you protection over a shared infrastructure. But when you build L3 VPNs over a shared infrastructure, this could be an alternate choice. It basically solves the problem of scalability, because think about how many site-to-site VPNs you would have to do. The advantage of building an L3 VPN would be scalability, because now I could have multiple providers, or in fact, multiple customers connecting to a provider, and they could go over the shared infrastructure and connect to remote sites. Adding a new VPN or a new customer or a new branch office does not really require much configuration. The only change that you would probably have to do would be on the PE side, which is the provider edge. The customer just runs maybe a routing protocol with the provider. It could be OSPF, it could be static routes, it could be ISIs, it could be EIGRP, or it could be BGP. Most probably, the customer would normally run either a default route to an ISP or BGP. I don't really see a customer running like an OSPF with a provider. Now, obviously, for us to build this L3 VPN, what are the prerequisites? What should we do? What should we configure within the ISP infrastructure to support or allow customers to connect, which are probably geographically separate? So the core components required to build the L3 VPNs, the first thing is that the ISP should have some kind of an IGP running within his infrastructure, which normally would be the case. Most probably ISPs would run either OSPF or ISIs. I don't see EIGRP being run within the ISP. It's either going to be OSPF or ISIs. So you should have some kind of an IGP running within the infrastructure of the service provider. That's the first thing. We should have some kind of an MPLS so that packets don't get dropped, because you would never have BGP on every router within the ISP infrastructure. You would never have BGP on all the routers. You'd probably have BGP on the edge, the PE routers. They would probably be running BGP, but you would not be having BGP on thousands of routers within the infrastructure. So we should have either MPLS or maybe segment routing within the ISP infrastructure. The third prerequisite would be to establish a BGP neighborship between all the PE routers. Now, again, this could be like a full mesh, which again would not be the case. Normally, you would have route reflectors. You'll have all the PEs peering with a route reflector, which could be a central point. And however, in our design, we would not be doing that. It's going to be a pretty basic implementation of L3 VPN, where we would just have 2 PE routers. So we need a BGP neighborship between the 2 PE routers. Now, what kind of an address family would we need, or what kind of a BGP neighborship we would need between our 2 PE routers? The first one would be maybe an IPv4 address family BGP neighborship, which could be used to exchange global routing table. And we would have a VPNv4 neighborship to exchange routes which are not in the global routing table, but maybe in a VRF. So BGP has to be configured. Obviously, we would need to configure VRFs to segregate the customer because we don't want customers to be in this global routing table. Think about why we would need to do that. Imagine if you have overlapping networks. Let's say if customer A is advertising to the provider 192.168.1.0, and at the same time, customer B is also advertising the same network. So you don't want that to be in the global table. So you would have to separate or segregate different customers. So we would create VRFs on the PE to segregate different customers. And then obviously we run a PE-CE routing protocol. Like I said, it could be OSPF, it could be EIGRP, it could be RIP, it could be ISIs, could be static routes, or could be BGP with the customer. Obviously, in your CCIE service provider, you would probably be tested for BGP as the PE-CE, or maybe OSPF. You would not be tested for EIGRP in the new blueprint. So in our case, in this webinar, we would be running BGP between the PE and the CE. The last thing that we need is redistribution. We do need to configure redistribution if your PE-CE was maybe an IGP. Maybe I was running OSPF with the customer. In that case, yes, I would need redistribution to redistribute the OSPF learned routes into BGP so that I can send those routes to the remote PE. Now, obviously, a few things that you need to keep in mind when you create the VRFs would be, we require a route distinguisher. So a route distinguisher is basically a 64-bit tag. It's basically a tag value, which when the PE receives the routes from the customer, he inserts that tag, which is 64-bit, 8 bytes, and the prefix is tagged with that route distinguisher. It has to be unique for every customer, so you cannot have two VRFs having the same route distinguisher. So think about it like, let's say if customer A is advertising 192.168.1.0 and customer B is also advertising the same thing. When the remote B gets the route, how does he know that this route belongs to customer A or customer B? How can he segregate those routes? That's done with the route distinguisher. So obviously, we still need a few more things. We still need to enable extended communities because we would have to import those routes from, which I'm basically learning from BGP. I would need to import those routes into the customer's routing table. So I need route targets also. So these are the basic prerequisites that you need, that you should think about when you build an L3 VPN. Obviously, inter-AS requires a few more things depending on how you're connecting to the remote service provider. Let's say if there were two ISPs which were connecting to customers. In that case, you would probably have option A, option B, option C, or carrier supporting carrier. So it depends on that. Obviously, we would not be doing that right now. So these are your basic prerequisites that you should always think about. So let's look at our topology that we would be working on. So here I have customer A and customer B, and let's pull this out. So I have customer A here, I have customer B here, and let's go and change this. All right. And I have customer B here, which is down. Now, router 1 is an iOS XZ, router 7 and router 8, which again, customers, they are iOS XZ, and the ISP is also running iOS XZ except for XR1 and XR2. So all of these routers are basically iOS XZ. The commands are a bit different between the XZ and the XR, but concept is still the same. So here, router 2 is going to act as a PE. XR1 is also going to act as a PE. XR2 would be customer end or custom edge, and router 1 would be the custom edge. Router 7 would be the customer edge, and 8 would be the customer edge. Router 3, 4, 5, and 6, they would not be PE routers. They are not running BGP. They would only be running an IGP and maybe MPLS or maybe segment routing. So these routers would be called as P routers, which are basically not running BGP. So this is going to be our infrastructure, which we would be building or configuring. We would also be looking at troubleshooting, like when I actually build the MPLS, we look at why would we not form maybe an LDP neighborship, how can we troubleshoot, where is the problem, we would look at all those things. Now, as of right now, nothing has been pre-configured except for IP addressing. IP addressing has been pre-configured, and OSPF within the ISP infrastructure has been pre-configured. The customers are not running anything, only IP address has been configured. The PE routers have they're only been configured with OSPF internally, not towards the customer side. So I only have OSPF internally within the ISP infrastructure at this point of time. So let's in fact start building this, maybe build the BGP neighborship between the customer and router 2 and XR2 and XR1 and maybe 7 and 2 and 8 and XR1. Now, even if I build the BGP neighborship, and let's say if router 2 and XR1, they are forming maybe a VPNv4 neighbor, or if my customer is in the global routing table, then IPv4 neighborship, my customer would have the control plane information. So all the routes from XR2 would be given to XR1. XR1 would give the route to router 2, and router 2 would pass those routes to router 1. So from a control plane perspective, yes, they have the routes in the routing table. But if router 1 does a ping to XR2, that's not going to work, because obviously R3 and R4, 5, and 6, they're not running BGP. So they would do a routing lookup, and they're not running BGP. So they would drop the packet. So I need some kind of a mechanism where, something like VPN, where router 3, 4, 5, 6, they don't do a routing lookup, but they do something else. So, and that's exactly what's going to happen with MPLS. So with MPLS, what's going to happen is that each router within the ISP infrastructure, they would establish LDP neighborship. LDP is my label distribution protocol. What exactly are labels? Labels are, think about labels as a representation for a prefix. So one label equals one prefix. It's obviously unique on the same router, but it could be same between two routers. So it's not unique between routers, but it has to be unique for every prefix on the same router. So think about it like this. If R2 advertises the customer routes to his BGP neighbor, it has to transit R3, 4, 5, and 6, right? It cannot just jump over the air. It has to physically transmit through 3, 4, 5, 6. Now, when 3 gets the packet, if R2 encapsulates the packet with maybe an MPLS label, In that case, R3 would do a label lookup, right? He would not do a routing lookup. And that's exactly what we want. So like I said earlier, that L3 VPN is like kind of a VPN, but it's not IPsec. We use BGP and we use MPLS for that. So now how are labels advertised? Think about it like IGP. Like for example, OSPF. So for me to give you a route, what's the first thing we do? You and me should establish a neighborship, right? You and me would form OSPF adjacency, and then I would advertise a route to you. You would put that route in your database and then in your routing table, and then your data plane uses the routing table to come back to me. So I advertise to you. Similarly here, all the routers 2 and 3, 3 and 4, 4 and 5, 5 and 6, 6 and XR1, they all will establish neighborship, which is called as LDP neighborship. They will establish LDP neighborship. Once they establish the neighborship, they will start exchanging labels representing a prefix. So first, you and me need to form LDP adjacency. Then I will send you a label for my prefix. And you need to use that label to come to me. And that's exactly what we would have to build. So if you remember the prerequisites, the first thing was ISP should have some kind of an IGP running internally, which we have at this point of time. The second thing was, okay, do we have MPLS running at this point of time within the ISP? No. So let's run that. Let's first build MPLS. Let's get our ISP infrastructure ready to establish LDP neighborship, to start exchanging labels. I'll also explain to you how the labels are advertised and how the MPLS forwarding table is built. So what I'm going to do is I will configure MPLS within the ISP infrastructure. And let's start with the router 2, which is my PE router. So I'm going to start with 2 and go all the way to 3, 4, 5, 6, and XR1. So what's the first thing that we need for MPLS? Ceph should be enabled, which I believe is by default, but you should have the habit of actually doing that, because sometimes maybe in the lab exam, from troubleshooting perspective, they may disable that. So have the habit of starting off from here. The next thing what I'm going to do is define MPLS label protocol as LDP. That's the second thing. So I'm going to use LDP, which uses port 646. One thing that you should keep in mind is that for LDP neighborship to establish, you must ensure that your router ID is reachable. Otherwise, you would not have LDP neighborship coming up. Okay. So what I'm going to do right now is I will configure my router ID to be my loopback. So if you look at my routing table right now, show IP route OSPF, I do have the routes of within the ISP infrastructure. I have 3, 4, 5, 6. So router 3 is 3.3.3.3, 4 is 4444, 5555, 6666, and XR1 is 19, 19, 19, 19. R2 is 2.2.2.2. So I would say MPLS LDP router ID would be loopback 0. You must use the router ID should basically be reachable. It must be a reachable address. Unlike OSPF, in OSPF, the router ID could just be any address. It doesn't need to be a reachable address. But in LDP, it must be a reachable address. I'll in fact show you by configuring a new loopback on maybe on some other router and showing you that how my LDP neighborship would get affected because of the loopback or the router ID not being reachable. So the first thing would be enable Ceph. Ensure you configure MPLS router ID, label protocol, that's again optional. And there's something that I always do, which is MPLS label range. I like doing this because it just becomes easier to troubleshoot when I do a trace route or a ping. It just becomes easier because I would see the labels and I know that the label is from a certain router. So from a lab exam perspective, it really makes sense. Maybe in production, you may not be able to do this, but because you may have thousands of routers. But in the lab exam, you probably have like 30 or 40 or 50 routers. So you can definitely do this. And you will never have routes more than 500. So what I normally do is I define a unique label range for every router. So let's say for R2, I would say 2001 or maybe 2000 to 2999. So that's a unique label range for router 2. The next thing that I would do would be to activate MPLS on my interface. Now I could do this in two ways. I could go to my interface. If you look at my interface, it is gig 1.23. So I could go to my interface and say MPLS IP. So this is one way of activating MPLS on my interface. Again, what if I have 20 interfaces? In that case, it becomes a tedious task for me to go and enable MPLS on every interface. So another way could be, since I'm running OSPF as the IGP within the ISP infrastructure, what I could do is go under OSPF and say MPLS LDP autoconfig. This activates MPLS for all interfaces which has OSPF enabled. So if I do a show MPLS interface now, you would see that I have MPLS enabled on gig 1.23. So one way could be I go to my interface and give the command MPLS IP. Another way could be I just go under OSPF or ISIS and say MPLS LDP autoconfig. This activates MPLS on all the interfaces. Whichever interface has OSPF running will have MPLS enabled. So now I have MPLS running on router 2. Let's now configure router 3, which is my P router. What's the first thing we do? We enable Ceph. Again, it's enabled by default, but have the habit of doing that. You don't want to waste 20 minutes of your time in the lab exam thinking about why is it not working, and then you realize that, oh, Ceph was disabled. So just have the habit of doing that. Start from here, configure your label protocol as LDP, label router ID, or range, in fact, 3000 to 3999. So I am giving a unique LDP range for R3, and then MPLS LDP router ID as loopback 0. Let's now go to router OSPF1 and say MPLS LDP autoconfig. This activates MPLS on all its interfaces which has OSPF enabled. So now I have MPLS towards R2 and towards R4. Remember, for you to establish this LDP neighborship, for you to establish this, you must have LDP on both the sides. Something like OSPF. You and me would not form OSPF adjacency if I activate OSPF and you don't. We both need to activate MPLS. Only then you and me would form LDP adjacency with each other. So now I have my MPLS running. Let's now go to router 4 and configure router 4. So again, IP is self, distributed, MPLS labeled protocol, LDP, MPLS LDP, route ID, loopback 0, and MPLS labeled range 4000 to 4999. Now again, this label range, it should be enough for the amount of routes that you have, and maybe about 30% more. Don't give a really low value because it's one prefix, one label. It's a 1:1 ratio. And let's go now to OSPF and say MPLS LDP autoconfig. So I should establish adjacency with router 3. The next thing that I would do would be configure 5. So I have my MPLS label protocol as LDP. Label range would be 5000 to 5999. And MPLS LDP route ID as loopback 0. Router OSPF 1. MPLS LDP autoconfig. Next, we have router 6, and then we have XR1, which is going to be left. So IP self and MPLS labeled protocol, LDP, MPLS LDP route ID loopback 0, and MPLS labeled range would be 6000 to 6999. Lastly, enable OSPF or enable LDP. So MPLS LDP autoconfig. You don't really need to do autoconfig on all the routers. You could do a mix and match. It doesn't really matter. You could have autoconfig on one router. You could have MPLS IP on the interface. The point is that you should have MPLS enabled on both the sides of the link. Only then you would establish LDP neighborship. The last router that I have within the ISP, so I've configured 2, 3, 4, 5, and 6. The next thing left, or the last one left within the ISP would be XR1. And you never enable MPLS towards the customer side. MPLS is only within the ISP infrastructure. So now I have XR1. For XR1, the commands are a bit different. So you don't really have to enable Ceph. So the first command would be MPLS LDP. And then we define the router ID, which again should be a reachable address. Let's do 19.19.19.19. And let's enable address family, IPv4. And finally, activate MPLS. So that's going to be interface. So this is something like MPLS IP on iOS XZ. If you do want to do autoconfig, you can still do autoconfig the same way. You could go back to router OSPF1 and give the command MPLS LDP autoconfig. So that command is pretty much the same. However, if you are using autoconfig, you still have to do MPLS LDP and address family. You still have to do that. You don't really need to do interface, because if you're doing autoconfig, you don't need to do that. So the interface would be, So interface would be gig0000.619. In fact, what I should do is before I give this interface, before I activate MPLS, you should always define the label range first. Because if I don't define the label range, then XR1 would allocate a label starting from 16, and I would have to probably clear my MPLS LDP neighborship or maybe reboot the router. So maybe I'm going to go back, exit out, and give the command MPLS label range, and let's define a unique range, 19,000 to 19,999. Go back to MPLS LDP and give the command interface gig0000.619, which is towards R6. Finally, hit commit, which activates MPLS on my interface towards R6. And I should see a message coming up which says LDP neighborship has come up. So now I have MPLS running on all the routers within the ISP infrastructure. If you remember, I told you that your LDP neighborship would not farm if your router ID was not reachable. Let's confirm that. Let's go back to any one router, maybe R3, and I will go and create a new loopback. Let's create loopback 1. And this loopback would not be advertising OSPF. So let me first check my OSPF, show run section router OSPF. In fact, I have network 0000. I'll change that so that I don't have MPLS or in fact OSPF on the new loopback. I'll remove this and let's do network 20.0.0.0.255.255.255 area 0 and network 3.3.3.3 area 0. So now I have OSPF only on my internal network and my loopback. Let's create that new loopback. Let's give an IP address 33.33.33.33. So this loopback is not running OSPF now. It's not running OSPF. Let's go and change my router ID. MPLS LDP router ID to be loopback 1. And in fact, let's do a force. There's no preemption. So even if you give the command MPLS LDP router ID loopback 1, it would not take effect unless you clear your MPLS LDP neighborship or reboot the router. But if you do force, it actually changes your router ID immediately. It's something like you doing a clear IP OSPF process. So now if you see, my router ID is loopback 1. Did my MPLS LDP neighborship, did it come up? I don't have any neighbors. I do not have any neighbors. What's the reason? Because the router ID is not reachable. So I would not be able to farm the neighbors. So now I have two choices. Either I advertise that loopback in OSPF, or I change my transport mechanism for LDP to use another loopback, but my router ID would still be loopback 1. If you look at, let's say, router 5, if I do a show MPLS LDP neighbor on router 5, look at my router ID. My router ID is 5555. My TCP connection is on the router ID. That's why it must be reachable. So what I would do is either advertise that loopback in OSPF, or maybe I could go to my interface and give the command MPLS LDP discovery transport address would be the interface. And same thing for 34, use the transport address as the interface. My LDP neighborship should come up now. So what's going to happen is that my router ID is still going to be loopback 1, but my TCP connection is going to be on my physical interface. I could give my loopback 1 or loopback 0 also here. Instead of specifying interface, I could give loopback 0. So if I do a show MPLS LDP neighbor, you would see that my router ID is still 33, 33, 33, 33, but my TCP connection is from router 2's router ID to the physical interface. Okay, it's the physical interface because I changed the transport to be my physical interface. By default, it uses the router ID as the transport. That's why your router ID must be reachable. It has to be reachable. Another thing, it's in fact pretty easy or straightforward to actually troubleshoot an LDP neighborship issue. Yeah, you could go and do a show MPLS LDP neighbor, but imagine if you have like 100 routers. I cannot go to all 100 routers and do a show MPLS LDP neighbors. Do I have my neighborship? There should be a better way to identify where the problem is. So, for example, let me go back to this diagram, and I will maybe disable MPLS here on this link. Just this link, okay? And we'll try and identify, how can we identify where is the break between two routers where my MPLS is broken? How can I identify that? So let's go back to router 6. In fact, if I go to my PE router right now and do a trace route to 19, 19, 19, 19, which is the remote PE, sourcing from my loopback, I should see MPLS end to end. So I have an MPLS here, I have MPLS here, here. I don't see MPLS here because PHP happens, which is your penultimate hop-popping. So it happened at R6. But right now my MPLS is not broken. Everything is okay. Let me go back to R6 and go to my interface 619 and say MPLS LDP IGP autoconfig. Let's disable that. So on that interface, on that specific interface, I'm not running MPLS. The reason I had to give this command was because I was using autoconfig. So when you use autoconfig, it activates MPLS on all interfaces which has OSPF running. So if you want to disable on a certain interface, the command would be no MPLS LDP IGP autoconfig. So on that interface, now I'm not running MPLS. So if I do a show MPLS interface, you would see that I'm only running MPLS towards R5, not towards XR1. Obviously, if I go back to R2 now and do a trace route, you would see that I still see everything okay here. If you see, I still see everything okay here, 6004 and then PHP. But is there a break in MPLS? Yes, there is an LDP neighborship which is broken between 6 and XR1. Maybe I could do a ping, and let's do a ping MPLS IPv4 to 19, 19, 19, 19, 255, 255, 255, 255, sourcing from 2.2.2.2 Verbose. What do I see? I see the flag as B. What does B say? B says unlabeled output interface. And it tells you that the packet was okay, reply was received, packet was okay all the way up to 20.5.6.6, which is R6. So up till R6, everything was okay, absolutely no problem. But outbound interface of R6 does not have MPLS, which you can see here, that unlabeled output interface. So you see, it's pretty easy to identify a break in your MPLS by just doing a ping MPLS. And you would know where the break is, just directly jump to that router and fix your MPLS. So I could directly go to R6 and fix that. Let's go back to interface gig 1.619. Maybe I could do an MPLS IP here, or I could remove the IGP autoconfig. So now that I have MPLS up and running again, if I go back to 2 and try the trace route, I should see ping. So now I know that PE to PE, everything is okay. So my ISP infrastructure is successfully configured for MPLS. So this was the second core requirement. One was running IGP, which we already had pre-configured, and the second was running MPLS. Now, how are these labels advertised, which we need to understand? If I do a trace route, I can see all these labels, right? 3007, I know it's from R3. 4004, I know it's from R4 because I gave a unique range. So it just becomes easier to troubleshoot when you look at the labels. I know it's from R4. This one is from R5. It just becomes easier. So how are these labels actually advertised? Let's in fact see if we can draw a diagram. Maybe, let's say I have router 2 here, or in fact I have a customer here, router 1. I have router 2 here. I have 3. I have 4, 5, 6, and XR1, and then a customer XR2. So this was my ISP, which was running OSPF and MPLS. I should have a BGP VPNv4 neighborship. This would be BGP VPNv4. Customer may run whatever. Maybe he runs IPv4 BGP. This would be IPv4 BGP. And let's look at how these labels are actually advertised. So I'm going to draw the MPLS forwarding table and explain how the labels are advertised and then how the data plane uses that label. So I have my routers here. So these are my routers. I have local label. I have outgoing label. I have the prefix. Okay. Seems like something is wrong. Okay. So I have my prefix and interface, and finally next hop. Okay, this would be router 2, router 3, router 4, router 5, router 6, and XR1. Okay, now my BGP neighborship between 2 and 6, or 2 and in fact XR1, this neighborship should be between XR1. So it's all the way here. So my BGP neighborship between 2 and XR1, there is another prerequisite that you would need. Your neighborship must be on the loopback. It should not be on the physical interface. It should be on the loopback, because otherwise your penultimate hop popping would happen one hop earlier. That's why your neighborship must be on the loopback. So let's assume that R2 and XR1 were establishing BGP neighborship on the loopback. So R2 is going to advertise a label representing his loopback. He would advertise a unique label for that loopback. And that label, because this loopback is directly connected to R2, R2 advertises a special label, which is called as implicit null. The label number is 3. So he advertises a special label to his neighbor through LDP that this is a directly connected interface of mine. It's a special label which I'm giving you, which is called as implicit null. So whatever he advertises, he puts that here. And that's going to be blank, which basically means that it's an implicit null label, label number 3, for the prefix 2.2.2.2, which is the loopback of R2. When R3 gets this special label, he puts that in the out column, and the special label was implicit null, which basically means pop label. Now, the meaning of pop label is remove just the topmost layer, remove just the top layer, and whatever's inside, forward that ahead. So he puts that pop label here for the prefix 2.2.2.2. On which interface did he receive the advertisement of the label? On gig 1.23. From which neighbor? From maybe 20.2.3.2, which is R2. Now, R3 has to advertise that prefix or a label for that prefix to his neighbor, which is R4. Is that loopback 2.2.2.2, is it directly connected to R2 or to R3? No, right? So he cannot send an implicit null. He has to advertise a label for it. Let's say he advertises 3001. He puts that here and advertises to his neighbor R4, which comes here. Again, 2.2.2.2 on gig 1.34 from 20.3.4.3. R4 does exactly the same thing. He advertises a unique label for that prefix to his neighbor R5, which goes here. This is the same. This is gig 1.45 from 20.3, or in fact, this is 4.5.4. Excuse me. And then R5 advertises to his neighbor. This is the same. Gig 1.50. In fact, this was 34. And 5 is 45. This is 56. 20.5.6.5, and 6 will say, let's say 6001 to his neighbor XR1 6001. This would be gig 0-0-0-0.619, 20.6.19.6. Now XR1 will also create a label for that prefix, maybe 19,001. But that label here is irrelevant because there's no neighbor behind XR1 at this point of time. In the future, if a new LDP neighborship comes behind XR1, then he would advertise 19,001 to that neighbor. But at this point of time, as per this diagram, it's irrelevant. So this is from a control plane perspective. Now from a data plane perspective. So XR2, he has learned the routes of R1 through BGP, right? Because R1 advertises via BGP to R2, R2 advertises to XR1, XR1 gives the route to XR2. So let's say XR2 does a ping to R1. Is there MPLS between XR1 and XR2? No. So he sends an IP packet. Because XR1 receives an IP packet, what does he do? He does a routing lookup, directly a routing lookup. Do I have routes to R1? Yes, learn through BGP. My next hop is 2.2.2.2. To reach 2.2, I must use IGP OSPF and forward the packet to R6. However, on the link between XR1 and R6, there is MPLS enabled. So I cannot send an IP packet. I must encapsulate the packet. So now XR1 does an MPLS lookup that to reach the destination R1, my next hop was 2.2. To reach 2.2, I must encapsulate the packet with a label 6001 and forward to R6. So now XR1 encapsulates and forwards an MPLS labeled packet 6001. What does R6 do? Does he do a routing lookup? No, because he received an MPLS packet, MPLS labeled packet. So he does an MPLS lookup. If I receive a labeled packet, which is 6001, what do? I swap the label with 5001 and forward it out this interface to this neighbor. So R6 swaps the label and forwards to 5, and this would still be IP, and this would be 5001. R5 does exactly the same thing, swaps the label, IP 4001. R4 does the same thing, IP, and this would be 3001. When R3 gets an MPLS labeled packet 3001, what does he see? He sees that, okay, if I receive 3001, I should do a pop label. Pop label means remove the topmost layer and forward whatever's inside to the neighbor. So now he does a pop label and forwards IP packet to R2, and R2 does a routing lookup and forwards an IP packet to customer. Now this is when there is no VPNv4, everybody's in the global routing table. Excuse me. But what if I want to segregate the customer? So maybe I go now, this time I go and put this customer in VRF A, and I put this in VRF A. Now, since the customers are in the VRF now, which is not in the global routing table, 2 and XR1 need to establish VPNv4 neighborship. Only then they can exchange routes or VPN labels. So in this case, what's going to happen, my MPLS label is my transport label, and my VPN label is the label which is below the transport layer, which is basically my VPN label. If you look at the VPN label, it is 96 bits because it consists of route distinguisher, which is 64-bit, and the IPv4 prefix, which is 32-bit, so totally 96 bits. So what's going to happen? The VPN label is not advertised through LDP. So R2 would never advertise a VPN label to R3 because R3 is not his VPNv4 neighbor. R2 only has one VPNv4 neighbor, which is XR1. So R2 would advertise a VPNv4 label, a VPN label representing the prefix of the customer. So he would basically, let's say he puts 2, and you would see V here. V indicates VPN label. And this is going to be, outgoing label would be no label. The meaning of no label is remove all the layers and forward IP packet to customer. The prefix would be customer's routing table, 1.1.1.1. Interface is gig 1.12, 10.1.2.1. And this VPN label is not advertised through LDP, it is advertised through BGP. So R2 advertises directly to XR1 through BGP. So only XR1 would see 2.2.2.2 for the prefix 1.1.1.1. And obviously his next hop would be 2.2.2.2. And this would be gig 0.0.0.0.19. You would not see, in fact, you would not see this in this would be in the BGP label table. It's not in the MPLS forwarding table. If I do a show MPLS forwarding table, you would not see this. This is in the BGP table. So now how is the packet flow going to be? Again, what's going to happen, the difference is going to be here. So customer sends an IP packet to XR1. Because XR1 receives the packet on a VRF enabled interface, he must tag the traffic with the label which the remote PE has advertised to him. What's the destination? XR2 is trying to reach 1111. To reach 1111, XR1 knows that R2 had instructed him that if you want to send packets to my customer, you must encapsulate with a VPN label called 2.2222. So now XR1 encapsulates with 2222, which is my VPN label. However, R2 is not directly connected. He must transit through R6, 5, 4, and 3. So there has to be an MPLS label, a transport label on top of that, which is going to be 6001. That's my 6001 here. And finally, it goes to R6. R6 swaps the label. So IP remains the same. VPN remains the same. This would change to 5001. Same thing happens here. IP, this would be 2222, and this would be 4001. Same thing happens on R3. IP, 2222, and 3001. When R3 gets it, what does he see? If I receive 3001, what do? Pop label, remove the topmost layer. So he removes just the topmost layer and forwards a VPN labeled packet to the remote PE R2. So R2 gets 2222. So now R2 does a lookup in his table, in his MPLS table, and he sees that if I received a VPN labeled packet, do no label and forward out this interface to this customer. And he forwards an IP packet to customer. So this is the scenario happening behind the scenes when I have MPLS running and I have VPNv4. So let's now go back to our routers and start building the L3 VPN. So the first thing that I would do would be, I would start with the customer. Customer is going to be running BGP. As per the diagram, the customer is running BGP AS120 on R1. Let's run BGP. So router BGP 120, Neighbor is going to be my ISP 10.1.2.2. Remote AS is 100. And let's advertise all my routes, redistribute connected. Let's also configure, in fact, R2 now. Excuse me. On R2, there are a few things that I would need before I build BGP. So think about these as steps. Always remember these steps. Step number one, once you've configured OSPF internally in the ISP infrastructure and MPLS is done, then for L3 VPN, the first step should be to create a routing table for the customer. If I do a show IP route VRF star, this is my global routing table. There is one more routing table right now which is pre-configured called management. But these are my two routing tables, global routing table and some VRF which is pre-configured. So the step number one should be to create a routing table for the customer. That's done with IP VRF. Now I could do an IP VRF or I could do VRF definition. The difference is that IP VRF only supports IPv4 and VRF definition is address family based, it supports IPv4 and IPv6. So I could do a VRF definition, let's say A, that's my first routing table. Now every routing table should have a unique identifier, which is my route distinguisher. So RD, let's use 1:1. Usually you would want to use the service provider's AS number and then any number representing the customer. So normally you would use, because I'm configuring R2, which is the ISP, I would do 100:1. R1, 1 indicates R1 and 100 is my own AS. But it doesn't really matter, you can use whatever you want. Let's exit out. Let's create one more VRF definition B and give route distinguisher as 2:2. So now I have two routing tables created. Let's verify that. Show IP route VRF star. This is my global routing table. And then I have I should have the routing table of customer A and B. Now I don't see that. My routing table did not get created. The reason it was not created is because I used the command VRF definition, which is address family based. I did not activate the address family. If I gave IPVRF, then I don't need to define address family because it's only IPv4. But VRF definition is address family based, so I do need to activate address family. So let's go back to VRF definition A and give address family IPv4 and exit out. I don't need to activate address family IPv6. I'm not running IPv6. Let's do the same thing for B. Once I do this, and if I look back at my routing table, it should be created now. I should see routing table A, which you can see here, and routing table for B. There's nothing inside it at this point of time, but I have created my routing table. That's my step number one, creating a unique routing table for every customer. Let's do exactly the same thing on XR1. So we'll do simultaneously on both the routers, both my PEs. So on XR1, I'll create the routing table also. Now here, the command is VRF A, and then address family IPv4 unicast. And if you look at the route distinguisher, that's not there. It's not under my address family. if I exit out under the VRF, my route distinguisher, it's not there because the route distinguisher would be basically defined inside BGP. So the concept is the same. You still require a route distinguisher, but you don't configure this under the VRF. You configure this under BGP. Let's exit out. And let's create B and address family IPv4. Exit out. And let's do a commit. So if I do a show IP route VRF star, I don't see, oh, in fact, let's do A. So there are no routes. I don't see any routes in the routing table because I haven't added any interface, but I did create my routing table. So step one is always creating the routing table. So all I did was show run VRF. I just made two routing tables, A and B, for both my customers. Let's go back to R2 now and do step number 2. So step number 2 is moving the customer-facing interface from the global routing table to the respective routing table, to the VRF routing table. Right now, my customer-facing interface is in the global routing table, which you can see here, show IP route, connected. That's my interface connecting to the customer. That is in the global routing table right now. So step number 2 is moving that interface from global to VRFA. So that's going to be by going back to my interface and giving the command VRF, forwarding A, and it re-give your IP address. Same thing I would do for the customer B. So interface gig 1.27, VRF forwarding B, and IP address would be this one. So step number 2 is done, where I have moved the customer from the global routing table to their respective routing table. Let's verify that. If I do a show IP route, VRF star, I should not find the customer facing interface in the global routing table. It's no more in the global routing table, which you can see here. The only connected interface I have is the loopback and the link to R3. If I look at A's routing table should have one link, 10.1.2, and B's routing table should have one link, which is 10.2.7. So step number 2 is done. Let's do exactly the same thing on XR1. So here, my customer-facing interface this is for B, and this is for A, which is as per my diagram. This is A, and this is B. So let's do a config T. Interface gig 0000.1920. That's my customer A facing interface. Now, unlike iOS XZ, when I give the command VRF forwarding A, it automatically removes the IP address, and I have to re-give the IP address. In iOS XR, it does not remove the IPv4 address. So if I give VRF A and try and do a commit, it would fail because the IPv4 address is not removed. So you should do a no IPv4 address first, then do VRF A, and then re-give your IP address. Same thing I would do for gig 0000.819. I would do a no, then VRFB, and then re-give my IP address. and we can do a commit. So if I had not done this, no IPv4 address, then my commit would fail. And if I do if I check my configs, it's going to be basically showing me that the IPv4 address was not accepted. So you would need to basically remove your IPv4 address and then add VRFA. So step number 2 is done on both my PEs, R2 and XR1. Step number 3 is routing protocol with customer. What's my routing protocol with the customer? It's BGP. So running BGP with the customer. Let's go back to 2 and run BGP with the customer. Right now I have no BGP running. So router BGP 100. Is my neighbor in the global routing table? No, because I have moved the customer facing interface from the global routing table to VRFA, right? So that should be under address family, IPv4, VRFA, and then give your neighbor statement, neighbor 10.121, remote AS would be 120. I should establish a BGP neighborship with my customer. So if you look at my BGP config right now, the only thing that I have is BGP with the customer. I have no BGP between my PEs yet. So step number 3 was running BGP with the customer. Let's do the same thing on XR1. So router BGP. In fact, on XR1, we would need to do a few more things before I run BGP, because in eBGP neighborship, I need an RPL, a route policy, to at least allow all the routes, because by default, any routes learned from that neighbor would be rejected. So I would need an RPL. So, but to establish the BGP neighborship, I don't need an RPL. To accept the routes, I would need an RPL. So let's not create that right now. Maybe I'll just say router BGP 100, activate the address family IPv4, exit out, and then we can say VRFA. Here is where I would give my route distinguisher. Let's say 1:1. And I should activate address family inside the VRF also. And then neighbor would be 10, 19, 20, 20. Remote AS would be 120. And that should be enough. Let's do a commit. So it says that it's something failed. Let's look at show configuration failed. It says BGP detected the warning condition that the parent address family has not been initialized. So let's exit out and do a show run router BGP. Exit out, and address family IPv4 unicast, and VRFA. I should see router BGP 100. And so I've done the address family. I just did a commit first. And let's create the VRFA. I guess I'll need the VPNv4 also. I shouldn't need this. It depends on the version also. Let's go and do, let's activate VPNv4 also. Yep. Okay, VRF. So if I look at my config now, show run router BGP, all I have done, I had to activate VPNv4 also for the iOS XR for it to accept this command. And let's go and define my neighbor now. So neighbor would be 10, 19, 20, 20. Remote AS 120 and commit. So I should establish BGP neighborship. That's my config. I should establish BGP neighborship with XR2. I still haven't configured XR2. So let's in fact do that also. So router BGP 120 and address family IPv4. Let's do a redistribute connected. Neighbor 10, 19, 20, 19. Remote AS 100 and activate address family IPv4 unicast. I'm not putting my RPL at this point of time. So if I look at my customer BGP, that's my BGP on my XR2, which is the customer. So he's running a normal IPv4 BGP neighborship with the service provider. But XR1 is running a VRF enabled BGP, and I had to enable VPNv4 to establish that neighborship. So if I do a show BGP IPv4, or in fact, let's do BGP VRF A, and let's do unicast. Summary. My neighborship is up. My neighborship with him is up, but obviously I'm not receiving any routes. The routes are going to get filtered because I do not have an RPL. So we'll come back to that. So step number 3 is done, where the PE and CE are running BGP with each other. R2 is an iOS XZ. He should not have a problem. He should have learned customer routes. So if I look at this, he's learned about the customer. R2 has no problem. He learns about the customer. But XR1 and XR2 would not learn about each other's routes, or they would not learn routes because the routes get filtered by default on iOS XR. It requires a route policy. Only then he would accept eBGP routes. You only require route policy for eBGP, not for iBGP. So maybe we can add the route policy right now. So we are done with step number 3. So maybe we could do that. Let's create a really basic route policy. Let's name this pass and say pass end policy. And go back to router BGP 100 and go back to VRF A and neighbor was 10, 19, 20, 20. And inside my address family IPv4 unicast, I would give route policy pass inbound when I receive routes or when I send routes. Let's do a commit. Let me show you my router BGP config. So if you see now, under my neighbor, under my address family, I have said, use this route policy pass, which means accept routes from him and send him routes. So if I go back and do a show BGP VRF A, enter, I should have BGP routes. Learn from the customer. In fact, I have not configured XR2 with the route policy, so he's not going to be sending any routes right now. So I would need an RPL on XR2 also. So route policy, pass in and out. So show run router BGP. I have an RPL configured and I'm redistributing all the routes. So he should be sending these routes, show BGP IPv4 unicast. These two routes he should be sending to the customer, to the service provider. I have two routes learned from the customer. So step number 3 is done. So I'll repeat that. Step number 1 was creating the routing table. Step number 2 was moving the customer-facing interface into the respective routing table. And step number 3 was learning routes from the customer. So that could be through OSPF, could be through ISIS, GRP, static routes, or BGP. We are using BGP. So now both the PEs are learning customer routes. Now both the PEs should exchange those routes, correct? They should exchange those routes. Before I move to step number 4, we should configure customer B also. So I believe on R2 I did not configure customer B. So I will add that too. So address family IPv4, VRFB, neighbor would be 10.277, remote AS would be, I believe it is 78. And that should be enough on R2. And on R7, we will configure BGP, just a normal IPv4 BGP. Neighbor 10.272, remote AS 100, and redistribute connected. So R2 should be learning from both the customers through BGP. So going back to show BGP VPNv4 unicast all, you should be learning from both the customers. Let's do a summary just to see if my BGP neighborship came up. So I don't see any routes being learned. Let's do a show run section VRF. That looks okay. Let's look at 7. Show BGP IPv4 unicast. So he should be advertising these two routes to router 2. Now he got it. So I should see in my VPNv4. So I have 2 routes of customer A, 2 routes of customer B. Same thing on XR1. I'll configure the second neighborship also. So all I need to do is go back under router BGP 100, VRFB, RD would be 2:2, and address family would be 10. I believe it is 8.19.8. Remote AS would be 78, and then the route policy. So show run router BGP. That's my VRFB. It should establish BGP neighborship with R8. Let's verify with show BGP VRFA has the 2 routes, and V should have 2 routes learned from the customer. Takes a bit of time, but it should come in. And then we can move on to step number 4, which is going to be allowing both the PEs to exchange routes with each other. Now, for the PE router 2 and XR1, for them to exchange routes, they should be VPNv4 neighbors. Right now, they're not neighbors at all. Do I need an IPv4 neighborship? You don't need that for this design, because my customers are in the VRF A and B, right? There are no routes in the global routing table. But yes, if I had global routing table, if I wanted to exchange that as well as my VRF routes, then I would need 2 neighborship, IPv4 neighborship to exchange global routing table, and VPNv4 neighborship to exchange customer routes. So let's go back and verify. So now I have 2 routes from the customer. So step number 3 is done. Let's move on to step number 4, which was establishing a VPNv4 neighborship between the 2 PEs. So router BGP 100 neighbor. This would be, now this neighborship should always be on the loopback. It should never be on the physical interface. Otherwise, your penultimate hop popping would happen 1 hop earlier. So that's going to be loopback 19, 19, 19, 19. Remote AS would be, I believe, 100. Neighbor 19, 19, 19, 19. Update source loopback 0. And address family VPNv4. Neighbor activate. So this would enable 2 neighborship between XR1 and R2. It would enable VPNv4 neighborship and IPv4 neighborship also. IPv4 address family is enabled by default, unless I go and give the command no BGP default IPv4 unicast. If I disable that, then I have to go to address family IPv4 and give activate command to enable IPv4 address family. But by default, it's enabled. So I would establish 2 neighborship with XR1. IPv4 also and VPNv4 also. Let's go back to XR1 and do exactly the same thing. So router BGP 100 and give command neighbor 2.2.2.2. Remote AS would be 100. Update source would be loopback 0. So use the loopback as the communication interface. And finally enable address family, VPNv4 unicast, and that should be enough. So show run router BGP. You would see that I have my VPNv4 was already enabled earlier globally. I have my VPNv4 neighborship with that neighbor. If I want IPv4 also, I can give address family IPv4 also if I do want to activate IPv4 also. I don't need that for our design because I have no routes in the global routing table. So address family IPv4 unicast and commit. So if I look at BGP now, for this neighbor, I have both the address families. So going back to R2, I have neighborship is up with the remote PE. If I do a show BGP IPv4 unicast summary, I have IPv4 neighborship with XR1 and show BGP VPNv4 unicast all summary. I have VPNv4 neighborship also with XR1. So step number 4 is done. Now there's one last step left. One last step. That would be to enable extended communities. Now what's happening here is, let's do a debug in fact. Let's do a debug BGP VPNv4 unicast updates, and let's do a clear IP BGP star soft. So I received routes from this neighbor, right? But those routes, look at this this part. This is my route distinguisher and the prefix of the customer A learned from XR1. But it was denied due to extended community not supported. See, the route distinguisher only distinguishes the route. Okay, this route is for customer A or for customer B using the route distinguisher. But what do I do with those routes? I need to tell my router that when you learn these routes, put them in the routing table of the customer, which basically means I need to support extended communities, which is your route targets. I have no route targets configured at this point of time. So going back to show run section VRF definition. Excuse me. Let's go back here and go to maybe my address family IPv4 and give the command route targets both. Let's give any random number 120:120. It does not need to be same like the route distinguisher. And let's do the same thing for B. And let's give this as 78:78. Now, whatever I export, the remote PE should import. Whatever he exports, I should import. If you see now, I should accept the routes learned from the customer. Let's do a show BGP VPNv4 unicast all. So I have both my customers. I still haven't learned the remote PE's routes because I haven't configured the route targets on XR1. So let's go back to XR1, go to VRFA, under your address family IPv4 and give your import route targets as I think it was 120:120 and export route targets as 120:120. Same thing I would do for VRFB. And this would be 78:78. Export route targets 78:78 and commit. So if I do a show run VRF, you should see that I have my import and export, which is step number 5. And if I look back at R2 now, he should be accepting those routes, which you can see here that now I have 2 routes learned from that PE and 2 routes learned from that again PE for customer B, which means router 1 should have all the 4 routes in his BGP table. He should have, but he doesn't yet. But the PE has learned all the 4 routes. So customer A has all the routes, customer B has all the routes. From the PE's perspective, let's look at XR1. Show B has all the 4 routes and A has all the 4 routes. So from the PE's perspective, they both have all the routes of all the customers. But does the customer have the routes? The customer is not getting those routes. Why is that? Let's do a debug. Debug IP BGP updates. And let's do a clear IP BGP star soft. So R2, the PE, the service provider, is sending me those routes, which I can see here. He is sending me those routes, but R1 denied those routes because the AS path contains own AS. If I look at the diagram carefully, customer A, XR2, and router 1, they both are running the same AS, 120, right? What does the AS path rule say? That if I receive an update which contains my own AS, discard that update. So router 1, even though R2 sends him the route, router 1 discards those routes because it contains its own AS, which you can see in the debug that it contains my own AS. Now, how do I fix this? There are 2 ways to fix this. One could be the service provider could fix this with the AS override command, or the customer could fix it. So let's try the service provider fixing this. So I am going to go back to R2 and go back to my BGP under address family IPv4 for VRFA and give the command neighbor 10.1.2.1. When you give route to this neighbor, do an AS override. Same thing for VRFB. When you give routes to 10.2.7.7, do an in fact, let's not do AS override here. Let's not do it here. We'll do the other method. Customer will fix it. So what AS override does is the ISP will replace the customer's AS with his own AS. So if I look back at R1 now, show IP BGP, he should have the routes now in his BGP table. He should accept the routes, which he did. And look at the BGP table. Look at the AS path, 100 space 100. Earlier, it was 100 space 120. That's why R1 was not accepting it. But because I gave the AS override command, the ISP replaces the customer's AS with his own AS so that R1 does not see 120. And that's why R1 accepts it. Obviously, I have to do the same thing on XR1 so that XR2 receives the route. So here I would go back to router BGP 100, go back to VRFA, and under my neighbor, 10, 19, 2019, I think it was 20. And here go to address family IPv4, unicast, and give the command AS override commit. So the concept is still the same. It's just the command, you define that differently than an iOS XZ. Once I do this, XR2 should have those routes in his BGP table, which he has. And look at the AS path, it's 100 space 100. The ISP has replaced the customer's AS with his own AS. Now, obviously, customer B would also have the same issue, right? Because the AS contains its own AS. So another way to fix it would be the ISP does not do an AS override, but I tell the customer to accept routes which contains his own AS. That's something that you should never do. That's kind of dangerous. So you should not do that. But let's try doing that. I will go to 7. And I'm right now not accepting routes that contain my own AS. So go back to router BGP 78, neighbor 10.2.7.2, and here I would say allow AS in. So allow routes that contain my own AS. This is something that the customer would do. You should not do this because now you are allowing routes to come in which contains my own AS. This could cause an issue from a loop perspective. This is another way to fix it. Same thing, I could go to R8, router BGP 78, neighbor 10.8.19.19, allow ASN, show IP BGP. So I should now accept routes that contain my own AS. Most of the times, the service provider himself would do the AS override if he's connecting 2 branch offices which belong to the same AS. You should not do an allow AS in. Let's do a debug IP BGP updates, clear IP BGP star, soft, and see if I'm receiving the routes. It looks like I am not receiving routes on R8 from XR1, but he is sending to XR2 and he's receiving from R1 also. Let's do a show run VRF just to see if I have the import export, which is okay. And on 2, show run section run VRF. I think I gave this looks okay. Yep, so it looks good. Let's check my route policy. Show run router BGP. So it seems like my XR1 is not sending routes to R8. But we'll still test this with maybe with router 1. So you remember when I configured the L3 VPN, if you remember that when I was drawing that thing, you should see two labels, right? You should see a VPN label and you should see an MPLS label. So if I look at R2 and do, or in fact XR1, and do a show MPLS forwarding table, these are all my transport labels, and look at the label for this customer, 2020, which is the customer's route. It shows as V. V indicates that it's a VPN label. Who is advertising that? It is advertised through BGP. So if I look at R2, show MPLS forwarding table, I should not see that label for 2020. I should not see it here. What was the label number? It was 19010. So if I look on R2, it doesn't exist here in the MPLS table. But if I do a show BGP, VPNv4, unicast, all labels, you would see that for 2020, I have received outgoing label is 19010. So this comes through BGP. So if I look back at R1 now and do a trace route, or in fact, let's do a ping first, ping to 2020, source loopback 0, my ping works. And if I do a trace route to 2020, sourcing from loopback 0, look at the label stack. So IP packet came from customer, there's no label. Then R2 sent to R3 a VPN labeled packet and an MPLS transport label. R3 sent to R4, he never changed the VPN label, he only did a swapping for the transport label to 4004. 4 sent to 5, 5004. 5 sent to 6, 6004. R6 does a penultimate hop popping, which means do a pop label, remove the topmost layer, and he forwards a VPN labeled packet. There's no MPLS label now. It's only a VPN labeled packet to XR1. XR1 does no label, which means removes everything and sends an IP packet to the customer. So so this was basic L3 VPN implementation. And I hope you guys enjoyed the webinar. I will now answer some of the questions that you guys have. Let's go back to all right, so I see some questions. The PE reachability command. You could do a ping MPLS to verify MPLS issues. So if there's an LDP broken somewhere, you could do a ping MPLS, or you could do a trace route. Many ways to identify PE to PE reachability. The video is going to be available. I believe you should receive an email with the link to the video. So Ivan, from perspective of the MPLS, I was talking from perspective of the control plane, where we are first going to advertise label. So it goes from R2 towards XR1, and your data plane uses that MPLS forwarding table. Does that make sense? Because the thing is that it's like me giving you the routes first. So when we are building the MPLS forwarding table, see, control plane and data plane, they're always in opposite direction. So I give you routes, you build the table, and then your data plane uses that table to come back to me. So when I was doing the MPLS forwarding table, when I was actually drawing that thing out, it was from the control plane perspective, where how the MPLS forwarding table gets built, and then the data plane uses that. So when I do a ping, I was doing a ping from XR2 going to XR1 and using the MPLS table. The steps required for building L3 VPN is you must ensure that MPLS and IGP is running within the ISP infrastructure. Then you must have your routing table created. So VRF should be created for each customer. You should move the customer facing interface into the respective routing table. And you should have a PECE routing protocol, which could be anything, could be OSPF, could be BGP, could be a static route, as long as you learn the routes from the customer. And then you establish a VPNv4 neighborship between the two PEs so that they can exchange routes. And finally, it was where we enable extended communities, which was import-export route targets. So whatever I export, you have to import. I see another question. Can I have LDP protocol? Can I have RSVP instead of LDP? Yes, you can. iOS XR needs to use AS override. Correct. I need to use the AS override because he would not send it because it's different behavior from iOS XZ versus XR. The allow ASN doesn't work on XR. Then I see another question. Is customer B now receiving routes from PE? The customer B was not receiving routes from the PE because it was an XR versus an XZ. XR does not support allow ASIN, so I must do AS override, which I had not done. That's why he was not receiving the routes. I see another question. What's the difference between control plane and data plane? Control plane is like for example, routes. When I give you routes, that's control plane information. OSPF information is control plane information. When you do a ping, that's data plane. Can you extend the label range after you assign them? Yes, you can. So I could go and change my label range, but they would not take effect. I have to remove MPLS or reboot the router. I have to remove MPLS and then change the range, and then again, it should take the new one. Otherwise, you can reboot the router. All right, so you guys should receive an email with the video for this. It has been recorded, and you should receive a video, like an email which contains the link for that. I hope you guys enjoyed, and thank you for attending the webinar.